David Smith here with one more Flip Classroom math video. 3 tips before you start. First, you could speed up or slow down the playback if that helps you get through the video at your own pace. Second, you could pause the video at any time to catch up with your notes. Third, you could turn on the captions and watch my words go by on the bottom of your screen. Today's lesson covers the binomial distribution and variance. And we'll get into variance in just a sec, but I want to give you something that I think you'll be happy to have. Expected value. A couple lessons back we did that, and we had this calculation where the expected value is the sum of lowercase, or the notation is we're summing up the probability that big X ends up being little x. And there was a lot of calculating to do. Here's a super easy way. It's the same result. It's just the number of trials times little p probability of success. That's it. So expected value is n little p. So you can use that from here out. You don't have to do that longer calculation. It's nice to understand what we're doing, but you can just use this little calculation. Okay, now on to variance. Now, if you recall, if you did statistics and probability where you calculated all these different attributes for a data set, you'll remember that variance was one of those. And if you dig a little deeper, you might remember that variance is just standard deviation squared. That's it. So variance, standard deviation squared. Here's our formula. I'll get into that in a minute. Now, variance was one of our measures of the spread of data. So the bigger the variance, the more widely spread out the data is. Remember, we had mean and median and mode. All those things were measures of the center of the data, or the central tendency. So when we talk about a data set, we describe both things, the variance, the spread, and the central tendency. Now, in a binomial distribution, it's interesting to talk about the spread. How widely is it spread? So here's your formula. N, number of trials, times little p probability of success, times 1 minus little p probability of success. That's it. Okay, so I summarized those 2 rules we have. Here is the expected value for random variable x. It's just the number of trials times the probability of success. And the variance, again, for random variable x, is just the number of trials times the probability of success times 1 minus the probability of success. Okay, dokie. Let's do an example and some calculations. First off, we need to know this. This is sort of a definition statement. It says random variable x is in a binomial distribution with this many trials with that probability of success. So this has to be true. Now I'm going to specify it. Now it's binomial distribution, 10 trials, and we have a 0.35 chance of success. So what I want you to do is pause the video and calculate the expected value and the variance. Okay, let's see how you did. So my plug-in step for my expected value is just NP. So 10 times 0.35 is going to give us 3.5. That's the expected value. And then finally the variance is just 10 times the probability of success times 1 minus that same probability. And if you do all that math, you'll end up with 2.28. Okay, let's do a few more calculations with the binomial distribution and some probabilities in our current example. So I've just summarized that right here. Here is my straight up notation. You should be able to look at something like that and start answering probability questions like this one. What's the probability that we'll have 5 successful outcomes? So before I turn you loose, I will remind you, here is our formula for that. So probability of random variable x equals some number of outcomes is n over r times p to the r times 1 minus p to the n minus r. So now you have to figure out what the plug-in step would be for random variable x, in this case equaling 5 successes. So pause the video and do that and come back. Okay, so here we go. We've got n is 10. That's the number of trials. We're looking for 5 successes. So here's our combinatorics term. Then we have our probability of success. That's the lowercase p. That's 0.35 raised to the number of successes that we need, which is 5. 5 there, showing up in those 3 places, times the 1 minus the probability of success. So that gives us 0.65 to the n minus r. So we can erase that and we can just do this as 5. So your next step is to take this another step. see if you can figure that out. Actually, take it all the way through. See what you can get and come back. Okay, my first step was just to figure out my combinatorics term. So we have 10 over 5. That's going to be 10 factorial over 5 factorial times 10 minus 5 factorial, which is just 5 factorial times 5 factorial there. So I started my whole process of canceling. You know me, I like to work it with pencil and paper. So I did 10 times 9 times 8 times 7 times 6 times 5 factorial so I could cancel out one of my 5 factorials on the bottom. Now I could just take my calculator and do all the math, but I like canceling. So I took my 10, that's 2 times 5. I took my 9, that's 3 times 3. And I took my 8, and that's 2 times 4. Now I have everything to be able to cancel out the bottom digits that leave me with a 6 and a 7. So I do all this canceling, and I end up with 2 times 3 times 6 times 7 on the top, 1 on the bottom. That ends up being 252. Woohoo! So now you know the combinatorics term. Pause the video for a sec. What does that mean in our situation? The combinatorics term just tells us a certain thing. It means that there are 252 ways to have 5 successes in 10 trials. 252 ways. Now, if you tried to make a list to figure that out, forget it. I almost absolutely guarantee you that you'd miss some. And there'd be a ton. So don't even go there. Use your little trick with that. Okay, next prompt. Finish this problem up. You know this term. You can do these pretty quickly on your calculator. Finish that up and find the probability that we're going to get exactly 5 successes in 10 trials in our binomial distribution. Okay, let's see how you did. The rest is pretty simple. What I did is I got my calculator out. I figured out what 0.35 was to the 5th, put that there. And I did the same for 0.65 to the 5th, put that there. Multiplied it by 252, our combinatorics term. You run that through the calculator, you get 0.154, which is a 15.4% probability of getting 5 successes in 10 trials. Okay, here's another prompt. What is the probability that you're going to get between 1 and 3 successful outcomes? Notice this is less than 4, so it doesn't include 4. So what is the probability that you can get 1, 2, or 3 successes? So go ahead, pause the video, do that calculation, and come back. Okay, in case you were scratching your head, let me show you a first step. It's just the sum of all the probabilities. So probability of getting 1 success, 2 success, and 3 success. So we add those up. So here it is, probability that little x is 1, little x is 2, little x is 3. So now, for some practice, go ahead and do those calculations and bring that one on home. Okay, I saved you the grief of all the board work for each of these. Each of these would be as complicated as the whole last one we did, where it was just x equals 5. So I skipped all that stuff, or actually I did it, but I didn't throw it up on the board and explain it because that would take like another 10 minutes. I hope you gave it a try, and what you should have got is 0.0725, 0.176, 0.252. That adds together to get a 0.500, or a 50% chance of getting between 1 and 4 successes in this probability experiment. Now, before I leave this one, I want to point out something. You would think that the odds of getting 2 successes in 10 trials is higher than getting 1 success, because this is 9 failures. So this is better. And then you'll notice that getting 3 successes in 10 trials, that should be even a higher probability, because we're getting closer to the center. And sure enough, that's a higher probability. So you can always look at that, take that kind of view of it just to check for errors. Because time and time again, when I grade tests and quizzes, I see students not employing that check and missing mistakes. Okay, so think about that. Okay, let's get a little more complex. Here's a nice prompt for you. What is the probability that x is less than or equal to 4, given that x is greater than or equal to 2? So there's an important next step that relies on one of the probability rules that you got maybe 2 or 3 lessons ago. So pause the video and do that step. It's kind of a plug-in step. Okay, so here is an expression of our rule, that it's going to be the intersection of the 2 probabilities that are showing here over the given that probability that's in the second part of this expression. So now we have something we can use. What I would like you to do is a plug-in step with some of this information and that information and come up with your next step. Okay, let's see how you did. So what I did is I just realized that the top part, the intersection, is just all the probabilities that fit inclusively between 2 and 4. So that's just the probability of 2, 3 successes, and 4 successes. We're just going to add those up. That's the top. That's the probability of the intersection. So there's a trick for the bottom part. Instead of calculating probability of 2 successes, 3 successes, 4, all the way up to 10, that's a lot of probabilities to calculate. You can just subtract n is less than or equal to 1. So basically we're subtracting 0 and 1 success from 1 to get this bottom probability. So I rearticulated it using that trick. So now we can populate this with some actual numbers and get to our answer. Okay, let's take a look at the bottom of this fraction. We could start adding up the probabilities of 2 successes, 3 successes, 4, and so on all the way up to 10, but that's a lot of probabilities to calculate. Really what we want is we want 1 minus the probability of no successes and 1 success. So I rearticulated that as 1 minus the probability that x is 0 for no successes and x equals 1 for 1 success. So now you can pause the video and you can populate these with their probabilities, calculate it, and get to your answer. Okay, I'm not going to fill the board up with all the combinatorics terms and all the calculation terms. I'm just going to give you the summary. So if you add 2, 3, and 4 success probabilities together, you get 0.666 on top. And then on the bottom, if we subtract the probability of no success plus 1 success from 1, we get 0.914. Do my division, 0.728 or 72.8%. One last prompt. Now this is a little tough because this is going to ask you whether this event, the probability of getting 4 or less, is independent of the probability of getting 2 or more. So you have to pause the video for a sec and look at your rules for probability to figure out how to articulate a test for this. We're going to need to do some calculation. The calculation is actually pretty straightforward, but we need to do that to answer this question. Because what it means is that the probability of either one of these cannot depend on the other one. In other words, it doesn't matter whether you're greater than or equal to 2 in terms of the probability of getting less than or equal to 4. Okay, so check this out. Actually, nothing to check out yet. You need to write an expression that will allow you to answer that question. Okay, so the first statement is that if these are independent events, then the probability that x is less than or equal to 4 should be the same of the probability that x is less than or equal to 4, given that it's greater than or equal to 2. These two have to be the same for this to work. Now, this one, we already have our answer for. We did this last time. We found out that it was the intersection divided by the given that part on the bottom, and what we got for that was 0.728. So, we don't have this one yet. We need to find out what is the probability of getting less than or equal to 4. So pause the video, do that calculation, and check and see if it's the same as 0.728. All right, so I think the most complicated part of this calculation is to evaluate the combinatorics term. Again, I used the combinatorics over here. So over here, 10 factorial, 4 factorial, 6 factorial. I broke it out, canceled my 6 factorial. I broke it out by factoring 8 is 2 times 4, left the others the same, and I broke 4 factorial down all the way. I canceled, I multiplied, I divided, I got 210 for my combinatorics term. So that means there's 210 ways in 10 trials of getting 4 or less successes. Pretty cool. So 210 times 0.35 to the r, that's our 4, times 0.65 to the n minus r, which is 4 from 10, gives us the 6th power. Do that math and come back and answer this question for me. Are they independent events? Okay, when I crunch these numbers, I get 0.237. So it's not equal to 0.728. So these two events are not independent. Now that you've watched the video, take a moment to jot down any remaining questions so you can ask them in our next class. If you want, you can come back and watch the whole video again if that helps deepen your understanding. If you enjoyed the video, please click like or subscribe.